This is the third class on chemical kinetics. Today I will discuss the molecularity of reactions and the difference of molecularity from order, and then I will proceed to the zero order reactions. So the headlines will be, it is lecture number 3, molecularity of reactions and integrated form of zero order reactions. This is the topic of discussion of today's lecture. Already I have discussed or explained the rate equation or the rate law. Rate law is very much useful to the scientists who are doing research in chemical kinetics. It has manifold applications. I shall mention only the two important benefits of this rate equation. So actually, rate equation or the rate law have two important applications. One is practical importance, and other is theoretical importance. These are the two importance I will explain of this rate law or the rate equations. And in this case, actually, rate law gives you the dependency of the concentration of the reacting components on the rate of these reactions. So this is actually very important. If you can find out the rate of any reaction, if you have the concentration of the reacting components at that time, provided you should know the rate constant of these reactions. Suppose one example I can give you, the rate equation. The reaction is H2O2 and giving you twice water plus oxygen, and the rate equation minus half D H2O2 by dt, rate of this reaction in terms of this decomposition of the reactant hydrogen peroxide, and this will give you some constant which is called the rate constant. Rate constant is important for a reaction at a given temperature. It remains fixed. So and the concentration of hydrogen peroxide and single power, first order kinetics. It will follow the first order kinetics as the concentration, single power concentration will control the rate of this reaction. Or a rate, you can get this order. This is one, means this is the first order. If the hydrogen peroxide is double, then the rate of this reaction is also double. So from that you can conclude that the rate of this reaction is directly proportional to the concentration of hydrogen peroxide. K is a rate constant. K is constant for a reaction at a given temperature. So once you know the value of K, which could be determined experimentally, at any concentration of this hydrogen peroxide, you predict what will be the rate of this decomposition of hydrogen peroxide. So this is the practical benefit. By controlling the concentration of hydrogen peroxide, you can run the reaction at a speed or at a rate of your own choice. So this is the practical benefit of this rate law. And the theoretical importance is that scientists are never satisfied or remain satisfied with the determination of this rate of this reaction, rate law of this reaction. They search, they try to know in which path, what are the steps by which the reactant is converted into product. So most of the reactions are multi-step reactions, and suppose one example I will show you. This is the twice NO plus oxygen gas phase reaction, and giving you twice N2 twice NO2 twice NO2. This is the nitric oxide is oxidized to give you the nitrogen dioxide. So this step, this is the multi-step reaction or the complex reactions, and it will follow in several steps mechanism which we can call, and the detailed description of the paths by which this reactant is moving to the product is called the mechanism. And scientists will try to establish or propose a mechanism for this reaction. Suppose in this case, say twice NO side of reversibility equal to N2 O2. This is the first step. And second step, N2O2 plus oxygen, and giving you twice NO2, this product. So actually this reaction is having the three steps, and whether the mechanism is acceptable or not, whether the proposed mechanism of this scientist will be accepted or not, that could be determined by this rate equation. It is possible, I will show you in later classes, from this mechanism you can derive the rate equation. Derive the rate equation of this reaction. And if you find the derived rate equation for this reaction by this proposed mechanism becomes identical with the determined rate equation. Determined rate equation experimentally determined rate equation or the rate law is minus d O2 divided by dt equal to some constant into NO concentration square and concentration of oxygen single part. Means the second order with respect to NO and first order with respect to oxygen. This is determined. This rate equation or the rate law is determined. And it is also possible to derive this rate equation from this mechanism. If the derived rate equation becomes identical with this experimental rate equation, then the mechanism is accepted. And this is the theoretical importance of this rate law. Now I shall explain the molecularity of this reaction. Molecularity of this reaction. Molecularity means the number of molecules, ions, atoms participating in this reaction is called the molecularity of that reaction. The number of molecules or ions and atoms participating in this reaction is called the molecularity. So molecularity, some reactions are unimolecular, whenever one molecule is participating. Bimolecular, two molecules are participating. Termolecular, three molecules are participating. So molecularity is for an elementary reaction. For an reaction could be of two types. One is elementary reaction. Elementary reaction, and other is complex reaction. Elementary reaction means single step reaction, and it is the multi-step reaction. Very few reactions are elementary reactions, means one step, and in case of one step reaction, molecularity is the number of molecules or ions or atoms participating in this reaction. And for example, you can say the H I plus H I, two HI reacting, two gives, these bonds are begin to break, and it is the partial bond. This is the I, this is the I, and it is the activated complex. Whenever the two molecules will have sufficient energy and proper orientation, then these two molecules will form this activated complex, and then it will break as H plus I minus I. So this is the single step. This reaction, two molecules are participating, so it is the bimolecular reactions. And order of this reaction is also 2, experimentally determined. Order is determined only by experimental data. So for the elementary reaction, it is possible to assign the molecularity of this reaction. And in this case, molecularity and order are the same. But in case of complex reactions or multi-step reactions, it will proceed in several steps. Say N2O5 giving you twice, giving you NO2 plus oxygen. This is the first order reaction. I have seen. I have also shown you in my previous class. This reaction follows the first order kinetics. But this is not a elementary reactions. It proceeds in steps. In fact, most of the reactions will proceed in several steps. Say in this case, it is the N2O5 sign of reversibility, NO2 plus NO3, and second step, NO3 giving you NO2 and this NO3 giving you this NO plus oxygen, and this NO plus N2O5 giving you this 3N. So this is the first step, reversible reactions. This is second step, this is third step. So reaction follows in several steps. So this is the complex reaction. And you see, each step has its own molecularity. This is the unimolecular, this is unimolecular, this is bimolecular. So overall molecularity is meaningless. Overall molecularity you cannot decide for the multi-step reactions or the complex reactions. But order of this reaction you could assign. Order could be assigned, but molecularity of multi-step reactions you could not assign, could not identify. Every step will have its own molecularity. So this is the difference of the order and molecularity. And for these two reactions, in case of elementary reactions, molecularity can easily be identified. But in case of complex reactions, each step will have its own molecularity, but total overall molecularity is meaningless. But in case of order, both this reaction could be identified with this order. This is the, this is the second order reactions, this is the first order reactions. So, order, I have already told, order may be 0, 1, 2, 3, even negative. But molecularity will always be positive integers. one molecule is participating, unimolecular. 2 molecules are participating, bimolecular. 3 molecules are participating, molecular. Overall molecularity of a complex reaction is meaningless. Only molecularity you can give for this elementary reactions. Further, there is a difference. There is so many differences between the order and molecularity. For order is an experimental fact, or could only be determined by experimental data, by conducting the experiments. But molecularity is a theoretical supposition. It is obtained only from this theoretically proposed mechanism of these reactions. As the order is an experimental entity, so this order of a reaction depends on the experimental conditions. If the experimental conditions are widely varied, then order of this reaction may also change. One example I can show you: azomethane, CH3 whole 2 N2. Azomethane decomposes to C2 H6 plus N2. The reaction, this order of this reaction, or the reaction will follow the first order kinetics. This is the gas phase reaction. This is also gas. This is also gas. This is also gas phase reactions. Whenever the pressure of this reaction is kept moderate to high, it is the first order. When pressure is moderate to high, reaction is first order. But when pressure of this reaction chamber is low, reaction is second order. So the order of this reaction will shift from the first order to second order depending on the pressure you applied experimentally, and at which pressure it shift from first order to second order, I will show you in my later class. Now, however, I already told in my last class, each and the reactions are classified on the basis of this order. Some reactions are zero order, some reactions first order, some reactions second order, and so on. And characteristics of the zero order reactions will have the common properties, common characteristics. Second order will have also the separate common entities, common characteristics. But each and every reaction could not be assigned with this order. Each and every reaction you could not assign by order. In the combination hydrogen and bromine, whenever reacting, hydrogen gas plus bromine gas, or hydrogen plus bromine, giving you twice HBr. In 1905, Bodenstein, after a long research or experimental data, he proposed the rate equation for this reaction following the chain mechanism. And according to this Bodenstein's mechanism, the rate is found to be minus half the HBr concentration divided by dt equal to some constant K, and some constant K into concentration of hydrogen and concentration of Br2 to the power half, divided by 1 plus K dash concentration of HBr and divided by concentration of Br2. So from this rate equation is very difficult to determine the order of this reaction. Only whenever the reaction starts at the initial stage, this value is very small in comparison to 1, and in that case only you can find this order 1 plus half equal to 3 by 2, means the reaction will follow the third 3 by 2 order whenever at the start of these reactions. Now I am coming this integrated rate law. Integrated rate law. So long we have discussed the differential form of this rate law, but integrated rate law is very much advantageous to find the value of rate constant of this reaction, and also whenever the rate constant of this reaction is known, which remains fixed at a given temperature, the concentration of the reacting components you can calculate at any time from the integrated form of this rate equation. So this is very, very much useful. Integrated form of this rate law is more useful than the differential rate law of this reaction. We start the zero order reaction. Zero order reaction, the rate law, integrated rate law of zero order reaction. The differential form, suppose the reaction is A to P. A is the reactant, P is the product. So the differential form of the rate law is minus dA concentration by dt equal to K in K0, suppose concentration of A to the power 0. 0 substrate giving to this rate constant to indicate it is the rate constant for this 0 order reaction. So this is the concentration to the power 0. Since the reaction is, this reaction is following the 0 order kinetics. So this one is equal to this one. The value of this is equal to 1. So this is equal to K naught. Means the rate is constant. This is the constant, rate constant. What will be the graph? Graph here time, here the rate. This is the rate. Rate remains constant independent of time. Means all along this experiment, all along this reaction, in case of 0 order, the rate is fixed. Rate is fixed, rate is uniform, rate will not vary with this time. This is a peculiar case for this 0 order reaction. In other cases, I will show you the rate always decreases with this time. Next one, you can write dA equal to minus K naught and dt by separating the variables. Here the A concentration equal to minus goes here, so minus K naught and dt. Now we integrate. Integrating within limit. Within limits means definite integrals. When t, here integration, here t equal to 0. So concentration of A at 0 time is A concentration naught. When the time is t, the concentration of A is this one. So this is the two limits, this is the two times. So whenever we are integrating, it will give you the concentration of A minus concentration of A naught equal to minus K naught and T, or T minus Q. So changing the concentrations, the rate equation is A integrated form of this 0 order rate equation equal to minus K naught T plus concentration of A naught. This is the initial concentration of this reactant. This is the concentration of this reactant at the time t. K naught is the rate constant. So if you like to determine the rate constant, say determination of rate constant. K naught of this 0 order reactions. What for the determination we require the performance of experiment. What will be the experiment? At different time intervals, the concentration of A is to be estimated by using either chemical method or physical method. Chemical method by titration, by titrating with a suitable reagent, using some sort of indicator, and physical method. I've also told polarimeter. You can use the instrument or colorimeter or the pressure at a constant volume or volume at constant pressure if the product is gas, and so on. So you will have a table. Here T, time and concentration of A. Whenever time is 0, means initial time, it is the concentration of A0. When the time is T1, concentration of A1. And when time is T2, concentration of A2. When time is T3, and concentration of A3. So this is the table. These are the experimental data, or you can say kinetic data. These are useful data for our practical purposes. So many factors we can determine, we can find out from this kinetic data. So now what shall I do to determine this value of rate constant? Simply you draw a graph. Here the concentration of the reactant, which is remaining at a particular instant of time, and here it is T. Here the 0 time. So whenever the T is 0, means initial rate, initial concentration of this reactant, and suppose this is A0. And whenever, and this reaction, this equation is a linear equation, or y equal to minus mx plus c. So it will be a straight line having intercept c and negative slope. So this graph will be like that. Here, at this time, concentration of A equal to 0. So that means the reaction is over, complete reaction. And this time you can call the TC. TC means completion time. Completion time means after this time TC, all the reactants will be totally decomposed. The reaction is totally complete. So this one, here concentration of this reactant equal to 0. No reactants are there at this time. And also you can determine from this graph, you will see how many utility of this kinetic data you can have. So this one is A0. So this value is A0 by 2. Means the reactant, concentration of the reactant is cut in half. Now half decomposition, or half of the reaction is done. So at this concentration, the time is called, very popular, it is called T half. T half means half-life period. Half-life period means after the completion of this T half, the reactant is cut in half. means concentration of this reactant becomes half of its initial value. This is the half-life period. You can also determine, you can also calculate, you can also find an expression of this Tc and T half from this integrated form of this rate equation of zero order reactions. Say half-life period. Half-life period, which is called T half. So in this case, when T equal to T half, A concentration is A naught by 2. So here A concentration of A naught by 2 equal to minus K naught and T half plus concentration of A naught. Okay. Then rearranging this one equal to K naught T half equal to A naught minus half A naught equal to half A naught or T half equal to A naught by twice K. So half-life period of this reaction, it is the expression. But if you know this rate constant, if you know the rate constant of this reaction, you can find out the value of T half. And rate constant is also determined from this graph using this kinetic data. Here K naught equal to M. So this is this one, suppose theta. This straight line makes an angle with this x-axis, and so tan theta equal to gradient equal to minus K naught. So from this graph itself, you can determine the rate constant of this reaction, and the graph is drawn on the basis of this kinetic data. This gradient, tan theta is the gradient of this straight line, and this one is minus K naught. And once you know the K naught, initial concentration you know, you have taken the initial concentration at the start of this reaction, so T half also known. And the completion time and it is also peculiar. Only the zero order reaction will go to completion. In most of the cases, the order will never be complete. Only in zero order reactions, the reaction is complete, and Tc is the completion time at which the reaction is totally over. So you see, the half-life period is directly proportional to initial concentration. More the initial concentration you have taken, more time it is required for the reactant to cut in half, or for the half decomposition or half reaction, more time is required. Suppose here, here it is taken 100 gram, and from 100 gram to 50 gram, here half of the reaction, or half of 100 grams to decompose will take greater time than the time required for half decomposition of this reaction. Here half-life is double than this one. Greater the initial concentration, greater will be the T half. It is a very common experience. If you take this large amount of this substance initially, it will take more time for half decomposition. Very common experience. It is our very common experience. It is only possible in case of zero order reactions. Now I like to find an expression of this. Find the expression of this TC. Expression of TC, completion time. So when T equal to TC, concentration of A equal to 0. When T equal to TC, the concentration of A equal to 0. So here 0 equal to minus K naught TC plus concentration of A naught. So TC equal to concentration of A naught by K naught. You see, the TC is double of this T half, or TC you can write the twice T half. One thing I show you. Suppose here A naught concentration and 50% of A naught is there, means 50% decomposed. It is the concentration of half of its initial value. So this one is T half. Suppose T half is 10 minutes. 10 minutes. So from this to 0% of A naught means the reaction is complete. It is in this case T half equal to also 10 minutes. So from this one to directly this one, it is the TC and equal to twice T half equal to 20 minutes. 20 minutes. You can show by means of figure, by means of arrangement. And you know the order and molecularity, if you consider the zero order reaction is only, could not be elementary reaction. As for this elementary reactions, order and molecularity is same. So zero order means zero molecularity. Zero molecularity means no molecules are participating. How it is possible? So elementary zero order reactions will never be elementary reactions. It is always a complex reactions, multi-step reactions. And already said, multi-step reactions have no overall molecularity. Most of the zero order reactions are heterogeneous catalyzed reactions. Heterogeneous catalyzed reactions, examples I can show you to say twice NH3 and here tungsten and certain temperature is to be given. This is the tungsten powder which acts as catalyst. So it will give you N2 plus 3 H2. And similarly another example you can see another example. Twice N2O and this gold powder is catalyst. So in this case twice N2 plus O2. So these are the decomposition. This is gas, this one is gas, this one is gas, this one is gas, this one is gas and gas and gas. Heterogeneous catalyzed reaction are mostly the zero order reactions. Or some enzyme catalyzed reactions also found to be zero order with respect to the substrate, means the reactant. And the next one, I will show you some problems. Which are set in IT Jam. Problem 1. What is a zero order reaction with A0 equal to 1 mole per liter and K0 equal to 2 into 10 to the power minus 2 mole liter inverse and second inverse. This is the unit of this zero order reactions. What is the concentration of reactant after 10 minutes? This is minute inverse. 10 minutes. So this type of problem you can find out by using this integrated rate law. Here A equal to, say, A, you like to determine this concentration of A at a 10 minute equal to minus K0 is given here 2 into 10 to the power minus 2 mole liter inverse and minute inverse, and the time is 10 minutes plus A0 initial concentration is 1 mole liter inverse. So this will give you the minute inverse cancel. So 1 minus 10 multiplied means 0.2 mole liter inverse, and it is equal to 0.8 mole liter inverse. Means for this reaction after 10 minutes, only this amount is the concentration of this reactant after the time 10 minutes. Another problem. Problem 2. Problem 2. A chemical reaction is found to be zero order kinetics. Chemical reaction is found to be zero order. Zero order reaction with K naught equal to 2 into 10 to the power with K equal to 5 into 10 to the power minus 8 mole liter inverse second inverse. How long? How long does it take to change concentration from 4 into 10 to the power minus 4 mole liter inverse to 2 into 10 to the power minus 2 mole liter inverse. Note of interpretation. Means here time is required for changing the concentration 4 into 10 to the power minus 4 mole liter inverse to this one. So this equation from this equation we can calculate the value of this time for that change. Here K naught T equal to A naught minus A concentration. So actually A to P reaction, this is the initial concentration of this reactant and this is the concentration after the time T. So this difference is equal to concentration of this product. Concentration of this product. So you can write this one is concentration of T. So T or T equal to time required equal to 1 by K naught into concentration of T. So change in concentration, that means T2 minus T1 equal to 1 by K naught into concentration of P2 minus concentration of P1. This is the time required for changing the reaction from P1 to P2. So this is equal to 1 by K naught. K naught is 5 into 10 to the power minus 8 mole liter inverse, second inverse, and here P2 equal to, from this to this, means this is the P2 and this is the P1. This is the initial product. So 2 into 10 to the power minus 2 minus 4 into 10 to the power minus 4, and this one equal to 1 by 5. This one is mole liter inverse, both the cases mole liter inverse. So mole liter inverse cancel, second will go upwards. So this will be equal to T2 minus T1 will be equal to 1 by 5 into 10 to the power minus 8 into this value is say 10 to the power 5. If you consider the 10 to the power 5, so it will give you 1 by 5 into 10 to the power 8, it will go upside, and into 2 into 10 to the power minus 2 minus 4 into 10 to the power minus 4. If you do these calculations, this one second. If you calculate this one, then it will give you 1 point 3.92 into 10 to the power 5, 10 to the power 5 second. So this is another problem which has been set in IIT JAM. So this is all about these zero order reactions. But already I have said zero order reactions are very few. Most of the reactions are first order and second order. So we shall go detailed discussion of this first order and zero order reactions. In my next class, I will explain the integrated rate law of these first order reactions. Thank you all who are watching my video.